Hello, and welcome to this talk. I will be talking about algebra and geometry in quite general terms. I won't be talking very technical. So algebra and geometry both are very large parts of mathematics, and I am just trying in this talk to tell you that there is a strong connection between these fields, and also there is a strong connection between this field and other parts of mathematics, and also with other parts of sciences like computer science and mathematical physics. So let me start with sharing my slides here. So as I told you that these two fields are quite large parts of mathematics, but when they come together, they create a really powerful kind of mathematics. Now, in general, algebra studies algebraic structures. These are like groups, rings, and so on, which are made out of numbers and functions, matrices, and so on. For example, like just like integers or real numbers and so on. But on the other hand, geometry studies shapes of spaces. For example, the n-dimensional space over the real numbers, just like the three-dimensional space, and also subsets of these spaces. Now, there are many different kinds of geometries in mathematics. You can start, for example, from set theory, where all kinds of functions are allowed. But if you make things a little bit more special, you go into topology, where you allow only continuous functions. And if you go into differential geometry, you need smooth functions. And analytic geometry similarly needs analytic functions. And finally, we come to algebraic geometry, which needs polynomial functions. So what separates algebraic geometry, distinguishes algebraic geometry from the rest, is that we work mostly with polynomial functions. And in this talk, I will mostly be focusing on algebraic geometry, where there is the strongest kind of connection between algebra on one hand and geometry on the other hand. Now, you can define algebraic geometry in very simple terms as studying solutions of systems of polynomial equations and the geometric structures which are constructed out of this system. The subject itself, algebraic geometry, is a really amazingly beautiful and complex part of mathematics, although polynomial functions are in a way among the simplest kind of functions in mathematics. But it's just amazing that the mathematics that is constructed out of these polynomial functions, in fact, leads to some of the most complicated, the hardest parts of mathematics. The subject is related to many areas of mathematics and also beyond mathematics. Just as some examples here, is related to all kinds of algebra. For example, group theory, ring theory, linear algebra, representation theory, and so on. And it's also related to all other kinds of geometry that I talked about in the previous slide. For example, topology, differential geometry, analytic geometry, Diophantine geometry, which is basically number theory, but also related to statistics, where now algebraic geometry is used to construct certain algebraic models. Is related to mathematical physics, for example, through string theory, but also quantum field theory, and so on. It's related to computer science, for example, cryptography, and so on. So there is a long list, which I just gave some examples here. Let me now tell you a little bit about ancient roots of this field, algebraic geometry. It basically started in the ancient times from the Babylonians, where they knew how to solve equations of small degree. And they came up with these equations for practical reasons. For example, just let's look at this practical reason here, where we consider a rectangle where one side is x, the length of the other side is y. Now, it may happen that you know the sum of these two sides, x plus y, let's say this is a, and you also know the area of the rectangle. So that means that you know x times y. And the question is, can you find x and y out of these two information that you have? You know x plus y, you also know x times y. can you find x and y? And this can be translated into a problem as follows. So since we know that x times y is equal to b, and x plus y is equal to a, we can rewrite this in this single formula where x plus b over x is equal to a, which we can also translate it into this formula, this equation x squared minus ax plus b. So this is a two-degree polynomial with only one unknown, one variable x in it. We already know a and b, and we want to find x. So this is an example of like a 4,000 years old problem. This tablet, I suppose, shows maybe this kind of problem. But now, if you increase the degrees and if you increase the number of variables, not just one variable, not just degree 2 polynomial, but if you consider degree 3, 4, 5, 10, a million, and so on, then you come up with much more complicated kind of mathematics. This slowly over thousands of years led into the development of algebraic geometry. So one of the things that really was important, central to this development, was the fact that we can relate numbers on one hand, which are algebraic objects, to spaces, which are geometric objects. So from a long time ago, we already learned this thing, maybe even in almost primary school, where at least middle school or high school, where you can look at the points on a line, and each point will correspond to a number, one real number. There is a one-to-one correspondence. And if you go to the two-dimensional space or just a plane, then there is a one-to-one correspondence where every point now is given by two real numbers, not just one. And you can just continue this. You go into the three-dimensional space, the usual space that we are familiar with, and there every point is given by precisely three numbers, just like in this example. So this thing is a line, a plane, and a three-dimensional space we can imagine, and in a way we can feel. But you can, in an abstract way, you can generalize this to higher dimension, where now r to the n is just the set of points where the coordinates are real numbers. Although we cannot really quite imagine it, but at least we can work with it in terms of abstract mathematics. Now, algebraic geometry, in a way, starts with first choosing a number system, which more precisely means that we need to choose a field. Now, examples of fields or number systems in mathematics include these familiar examples, like the rational numbers, the real numbers, complex numbers, or finite fields, and so on. So finite fields are just integers mod some prime number. So once you choose a field, then you can start doing algebraic geometry, and the geometry will, in a way, depends on the kind of field that you work with. So yeah, we're starting with algebra, basically. That's the number system, is an algebraic object. And having chosen our field, then we can look at the polynomial ring. This is the set of all the functions in a certain number of variables, let's say n, where the coefficients of these functions, these are polynomial functions, the coefficients all come from the given field k, let's say the rational numbers. So still we are just working with algebra. And then the next step is to define the geometry. Now, a variety or a geometric space in algebraic geometry, so these are the main geometric spaces, is simply the common solutions of a collection of polynomial functions. You can even take infinitely many of them. It doesn't really matter, but it's the same if you just take finitely many polynomials. You look at all the solutions of this system of polynomials, and the solutions can be just considered, so these can be considered a point inside k to the n, this n-dimensional space over our field. So it depends on what kind of field we are working on. So starting with something which is algebraic, these polynomial functions, the whole polynomial ring, and then choosing some polynomial functions of our system, then we are led into something which is geometric. So if k, if the field is the field of real numbers, then it's not difficult to imagine that that R to the n itself is something geometric, and if you consider a subset inside this n-dimensional space, then it also has a kind of geometry. Although we need to define exactly what it means, what we mean by geometry, but there is no time to do it here. So just remember that you start with polynomial functions, you look at the solutions now consider them as a geometric space. So the goal is then to understand the geometry, the shape of this space in a local sense, but also in a global sense. And now there is actually also a compactified version of all these notions, varieties and spaces, which I'm not going to define here. The talk becomes a little bit technical, but just remember that there is a compactified version of these notions. So let's look at some simple examples. We have all seen this equation in high school. This is just the equation of a circle. However, the shape of the equation depends on what kind of field, what kind of number system you work on. If we work over the real numbers, this is exactly what we have seen in high school. The graph of this equation inside the two-dimensional space gives you exactly a circle. So a circle is something which we can define in other ways. We are very familiar with it, but we can associate to it an equation of this form. So that's where you see a dictionary between algebra and geometry. However, if you work over the complex numbers, the shape of this equation looks actually quite different. It's not a circle, but it's like a sphere with 2 points removed. We have to remove the points because we are not working with compact spaces. If we work in the compactified version, then we can also add these 2 points and we just get a sphere. But on the other hand, if we work over the finite field with 3 elements, in other words, just the integers mod prime number 3, then the shape of the space that you get from this equation is just 4 single points, 4 separate points. So the geometry actually is the way it looks like depends on the kind of field that we are working on. Let's consider some other examples. These 2 simple equations like t2 to the 2 minus t1 to the 3 has this shape here. The red thing here is the shape of this space. The black lines are the coordinates. These are the coordinates lined. But the red one is the space itself, which is defined by this polynomial. And you can also see that there is something strange going on here, which is that the curve kind of breaks at this point. And there is a good reason for this. But on the other hand, if we look at this equation here, again inside R square, then the shape of this equation looks like this, which is quite different. Again, this is the red shape, not the black one. But if you work over the complex numbers, for example, then the shapes will look different. So what we see here is inside R square. Now, if we make things a little bit more complicated, look at this equation of degree 5. Now we have 4 variables, not 1 or 2, but 4 variables. The degree is 5. The equation itself it looks kind of simple, not very complicated, but then what we get, at least when we compactify, what we get is something which is 3-dimensional in the sense over the complex numbers, but it actually is 6-dimensional over the real numbers. So we cannot really imagine it, in a geometric sense. But if we take a slice of this space, we get something like this, which is very familiar to people in all kinds of geometries, but also people in mathematical physics. It has become, in a way, like a symbol of string theory, because string theory needs these kind of spaces, which are called Calabi-Yau manifolds. Okay, now let's look at another example where we get singularities. We actually got singularities in previous examples, but let's look at this new one, where the equation is now t1 squared plus t2 squared plus t3 squared equal to 0. We consider the solutions over the complex numbers. this space becomes singular at this origin. Now, it's not so easy to define exactly. At least intuitively, I can tell you what singular means. It means that at that particular point, this space doesn't look like the most other points. But more, in a more precise mathematical sense, you need to take the partial derivatives and see that they all vanish at this point. But at least if you look at the shape, this is the shape, but this shape is drawn over the real numbers, not over the complex number. You can see immediately that at this origin, at this point, it's like that. It's like if you have two cones and they're attached together at this point. So that point doesn't look like the rest of the shape. So that's why it is singular. However, we can remove the singularity by some kind of operation, which is called a blow-up. It gives you something which is not singular anymore. It has no singularity. It replaces that point at the origin, that singular point, with something, at least in this shape here that I have drawn, looks like a circle. So there is a lot of interesting things going on when you even work with like the simplest kind of equations. Now, we can make things a little bit more complicated if we consider now x in the four-dimensional space over the complex numbers defined by this polynomial t1, t2, minus t3, t4 equal to 0. Again, this has a singularity at the origin. You can check it by looking at the partial derivatives. Now, similar to the previous example, if we do the blow-up, that kind of operation, we will get a new space W where the singular point is replaced by something else, which looks nice. More precisely, mathematically, that something else is isomorphic as a space to a sphere cross a sphere, but we are working over the complex numbers here. Now there are two projections from this space, this new space W, onto two other algebraic varieties, two other spaces. And when you put the whole thing together, you get a diagram like this. You start with X, you get W, you get Y1, you get Y2, you get a diagram of this form. And now both of these spaces, Y1 and Y2 on the sides, they are both of them smooth spaces. They contract something which look like a circle, each of them. Circle over the real numbers, but over complex numbers, they will look like a sphere. But this diagram that we get, if we forget about the W here, is something which is called an Atiyah flop. And this is an example of a very important operation in algebraic geometry. There is a more general operation called flip. But already this simple example can be viewed, it can be examined from so many different points of views in algebraic geometry, even from mathematical physics kind of point of view. So that's why algebraic geometry is so interesting, because starting even with simple things, you are led to really very interesting, complicated objects, and it relates to so many other things, not only algebraic geometry itself. Now, in the remaining couple of minutes, let me also give you another type of example where now this is related to arithmetic, to topology, and so on. This time we start with X inside the two-dimensional space. Now, for the moment, I haven't picked a field yet, so this is a little bit vague, but later we will need to take like the rational numbers and complex numbers and so on. This is defined by just one polynomial f in two variables, and the degree of the polynomial is d. Now, we assume that x and its compactification has no singularity. Then this compactified version over the complex numbers, it actually looks like this. It just exactly is one of this kind of thing, but there are infinitely many possibilities. So it's either it's just a sphere, or it's a sphere with one hole in it, or a donut, or it's a donut with more hole on it, so like three, or it can be many more. So there are infinitely many possibilities here. And the number of holes, interestingly, like here, the number of holes is 0, here is 1, here is 3. It can be calculated just by the degree of this polynomial. It's given by this equation, half of d minus 1 times d minus 2, which is called the genus of this space or polynomial. So it has a not too complicated kind of topology, but its arithmetic is very, very complicated. In general, it's very hard to see if there is any point in this space with coordinates in the rational numbers. An example of this, a famous example of this kind of situation is where we take f to be t0 to the m plus t1 to the m minus t2 to the m, where m now you can take it to be d, so the degree will be d. The arithmetic is very, very complicated, but what we know here, I can list it. If g is equal to 0, if there is no hole in this space, assuming that we have at least one point with rational coordinates, then there are infinitely many points with rational coordinates. But if there is only one hole in this space, then the set of all the points with rational coordinates, it forms an algebraic structure. It's an algebraic group, and it's an abelian group. It is finitely generated. This is an old and famous theorem. Now, if the number of holes in this space is 2 or more, then there can be only finitely many points with coordinates inside the rational numbers. And this is a very complicated, very difficult theorem from a few decades ago. Now, this is just, you could say that the simplest kind of situations. We have just one polynomial over two variables. If you increase the number of polynomials, not just one, but have 10 polynomials, and if you have like 50 variables, then you can imagine how complicated things can get. So that's why this field is so interesting, because its problems are so difficult. If you have difficult problems, then it usually leads to interesting and complicated mathematics. I think I don't have much more time to talk, so I will stop here, and thank you for listening.